So the resistance level of semiconductor material is decreased because of increased heating. So when more amount of current is going to flow, the resistance is going to become less. I mean, this is conceptually as per Ohm's law. So whenever the current is going to be high, the resistance is going to be less. So this resistance will in turn make the current to increase further. So if the current is going to increase, the power is going to increase. The power is going to increase, the temperature is going to increase. The temperature is going to increase, the semiconductor is going to be melted. So it is going to be a chain reaction. First thing, current will increase because of low resistance. Because of current is increasing, the temperature will increase. Because of temperature is increasing, again current will increase. So these all factors will eventually lead to a point where the semiconductor will start melting. The power dissipation in the BJT is given by PQ is equal to VC into IC plus VB into IB. So usually in normal BJTs, we will not consider the power dissipation for the base terminal. But here you see we consider the power dissipation in both the emitter and base terminal because both the currents are very high. Both the voltage is also very high. But only thing what is consoling is IB is still in microamperes, whereas collector current has gone to amperes. So that makes one assumption. What we can do is, since the base current is very small compared to collector current, I can approximate the power to be PQ is approximately equal to only the first term VCC into IC. I can neglect the second term. Even though IB is in microamperes and VB is going to be very large, the eventual product of these two things is not sufficient enough to get additive to the power dissipated in the collector region. So PQ is approximately equal to VC into IC. So this is the DC power. So if I'm going to give an AC signal, if I'm going to give a sine wave to the transistor, I have to find the power for one cycle. So I have to integrate from 0 to T. T is one full cycle of your sine wave. So I see the power is given by 1 by T integral 0 to T VC into IC. I'm finding the average power. Average now integrating and dividing by T. That is the average power. So the average power must always be kept low. So even though the power, DC power, which is coming out of transistor is very large, the average power has to be kept low to ensure that the transistor is going to be always stable. So the maximum power rated of the BJT is given by PT equal to VC into IC. This is the maximum power your BJT can withstand. So other things are available in the. We are going to see a graph where you will see the VC versus IC characteristic. So see this graph, VC versus IC characteristics. It is called as SOA. SOA is safe operating area. So in this graph, we are going to clearly say what is the safe operating area of your device. So you can see here, this is the maximum current your device can withstand. This is the maximum voltage sustained for breakdown. So any graph will be between 1 amperes of IC and 90 volt of VCE. Okay, so if you draw the graph, you have this case where this is the maximum power limit. This is the maximum power dissipation of transistor. You have second breakdown and the sustained VCE voltage. Okay, these graphs will clearly, so whatever be the operating point, it should be within this region. If it goes beyond this region, then the BJT is going to be unstable. This is called the safe operating area of your BJT. So safe operating area is bounded by the maximum current limit, the maximum power dissipation, second breakdown, and the sustained VCE value. So you see here, so it is bounded by all these things. The safe transistor is going to operate in a safe operating region, and the safe operating region is bounded by 4 parameters. One is maximum collector current, sustained VCE, maximum power, rated power of your BJT, and the transistor second breakdown characteristics. So you have to ensure that your BJT is always going to operate inside this SOA. SOA is the safe operating area. SOA is this shape. So whatever collector current and VC are going to mark, it should be inside this only. If the VC and the collector current are going to go outside this, then the transistor become unstable and breakdown might happen. So that's why they define the SOA is bounded by these 4 parameters. Okay, and this graph, it is given in normal scale. The same graph they have given in logarithmic scale. So logarithmic scale, if you see, the view is very good, and you can clearly identify the region of safe operating area of your transistor. Okay, but in normal scale it is a little bit difficult to view because the graphs will have multiple overlappings and coincidence happening. But the same thing, if you convert the axis into logarithmic scale, you can clearly view the area of the safe operating region. So the any point which is going to lie outside this SOA will damage your transistor. So you can move the point outside the SOA for a very short amount of time, but you should ensure that you bring back the operating point of transistor inside the SOA. So if the point is going to lie outside the SOA for a longer period of time, then the transistor is going to become unstable, or you will have breakdown happening in the transistor immediately. So you assume the point is somewhere here, the operating point is somewhere here. You are moving this point outside to this point, but you have to move it back here immediately. So if you are not moving this point immediately inside SOA, then you cannot have control over the working of your transistor. The transistor will go to breakdown. So that's what they are saying. The You can move the point outside the SOA, but it should be momentarily. Momentarily means for only short duration of time. So if you are going to keep the operating point outside the SOA for a longer and longer period of time, then you cannot expect stable operation of transistor inside that particular operating point, because they clearly mentioned SOA is the region where stability is guaranteed for your power BJT. Outside SOA, the stability is not guaranteed, or outside SOA, your device can be there only for a very, 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 very short amount of duration only. So you have to again bring back your device into the SOA region. SOA means safe operating area of the transistor. So in conventional transistors, we don't have this SOA region because all the temperature, voltage, current, and power are within the limits. But when you talk about power BJTs, these become very, very important because everything is going to affect the stability of your transistor. Okay.